The title of my presentation is Frames, but in reality what I want to do is to try to provide you a guided tour from linear algebra to computational harmonic analysis. So you may think, well, I know linear algebra quite well, and nevertheless I would be happy if when you leave this place after 1 week, your view on linear algebra has changed. So the first thing I will try to do is, I have written up here some programs that we're using. What I'm usually starting with such general talks is to start a time frequency toolbox, which is in this case the STX toolbox, which is has been put together at the Austrian Academy of Sciences at the ARI, the Acoustic Research Institutes. The director there is Peter Balac, who was one of my former students, and one of the first things he was deciding was to make this publicly available. So you can download it for free, and it's going now through the microphone of my computer, and what it does is very quickly, easily recognize. So you see, it's just doing a time. So it's a time frequency analysis and showing you at which time, which frequencies are relevant. So you can put it in hertz. So the range here is from 0 to 4,600 hertz. You can put it in different other scales, Spark scale and so on. We will hear a lot about these things. And you can also hear now or see my voice. I can try to speak very loud like a singer, so a lot of overtones, or can speak normally, then it's much more flat. And you can imagine also that somebody, an audio engineer, having such things available, may want to change it. He may want to say, well, my listening device is too much damping the high frequencies. So what he would do, he would enlarge and raise the high frequencies, or he would modify it depending on the loudness of the piece. If only the flute is playing, maybe the flute is a little bit pushed up and the bass is a little bit put down, or the other one. That's, from my point of view, a Gabor multiplier. So we're doing time frequency expansion of signals. We're doing something on the coefficients that we resynthesize. Usually I'm telling it in this way, a bad guy is distorting my nice classical music by such a device. And even if I watch him, I can say I can compensate it. So you have the question of composition of two Gabor multipliers. Is it the Gabor multiplier of the product symbol? So it's like Fourier multipliers. Fourier multipliers, you multiply, you have a diagonal matrix, you go back. It's not exactly the same thing. Why is it not the same? Well, because these systems are linear dependent. What does it mean they are dependent? They are frames. What is a frame? And later I will go to mathematical detail. Well, this is a frame. What you see is probably 5 fingers in the 3-dimensional space. So they are in general positions. Look at them. This is not a frame, because it's a flat hand. This is a frame for the linear span, which is a plane of redundancy 5/2. I'm talking about a 2-dimensional space, and I have 5 fingers. This is a frame of redundancy 5/3. So we have notions of linear systems in vector spaces which are quite useful. And so I will turn off now this computer and go to the linear algebra story. So kind of how can we view linear algebra from the computational point of view? And while I'm prepared another software package, I want to show it first because I will stay mostly with MATLAB. So this is in my list number 2, GeoGebra. GeoGebra grew out of a master thesis a couple of years ago at the University of Salzburg. Mr. Hohenwarte is now a professor at the University of Linz. And as you can imagine, GeoGebra is a mixture of geometry and algebra. Nowadays, I would say you can do everything that you have to do for school purposes with GeoGebra and also a little bit of linear algebra, polynomial plotting or so. So when you take linear algebra, then you know that a matrix is invertible if and only if it's, the coordinates are a basis. Now, another viewpoint is to talk about bi-orthogonal systems. So if somebody is giving you 3 vectors, you can in principle imagine that there's a bi-orthogonal system, because if you have 3 vectors, 2 of them span a plane, so you can make a perpendicular vector. And you can choose the length of this perpendicular vector to be just 1. Now, normally you don't talk much about bi-orthogonal systems, but you are talking about inverse matrices. So you put the 3 vectors in the matrix, and I just have to tell you, take the inverse matrix, take the rows of the inverse matrix, then you have it. We will go through this in detail. So bi-orthogonality is an important concept. You can imagine that we all learn and know orthogonal systems are very important. Well, these are just the self-bi-orthogonal systems. And as an output of just some demonstration I tried to give to the linear algebra students, I was starting to do a little bit of GeoGebra, and it was really something where I would say you should also try it. It's tempting. You do a little bit of demonstration. It's so easy that you're getting deeper into it. And that you, for example, I thought, I want to show what the rows of the inverse matrices are. So for me, it's the bi-orthogonal system. And well, for convenience, I take vectors, a 2 by 2 case, so a matrix of size 2 by 2, where I would randomly, dynamically change the entries. So you are giving me 2 unit vectors in the plane, but they should be in general positions. Now, GeoGebra is very good for this. I'm starting with a prepared presentation, but I could do it within, I don't know, 15 minutes from scratch. So I make a circle, and on the circle I put 2 points. These points are the points here, A and B. The good thing is if they are placed on the point, I can move them. So I can take these points and I can move the points. So the black arrows, so the arrows going U and V, going to A or B, are just the columns of a matrix. So we talk about now the inverse of matrices where the first and the second column are normalized. Very, very standard situations. Now, without much explanation, what I am showing you in the red arrows, you have the rows of the inverse matrix. So that's what I normally call the bi-orthogonal system. And the dynamical program allows me to move around and to see what happens if I change these entries. So for example, I take the point B and I move it around. So what you see immediately from such a picture, you don't have to know much linear algebra, is if I move them closer together, the red things are getting longer. Also, if I move them in almost opposite direction, they also go longer. And then you can go and say, well, when is the system self-bi-orthogonal? When are the rows of the inverse matrix exactly? And you know, of course, this has to be the case when it's orthogonal. So again, this would be a standard situation. And when I'm asking you, well, this 2-column system, the 2 black arrows here, which one is the closest orthogonal matrix? So the matrix which is in the natural sense, close in the sense of the R4, closest to it. What would you think about it? You would say, well, here the angle is acute. The bi-orthogonal system has to compensate. It has to be wider. So let's make a compromise. Let's something in between. Well, I will tell you that you should take the gram matrix, take the gram to the -1/2, then you get exactly this. Or you do polar decomposition and you take out the dilation part, and then you get also this bi-orthogonal system, which would be exactly in between the black and the red system. All these things should be understood, as I think, in the linear algebra sense. You should know all the time how to do it with MATLAB. And once you do it with MATLAB, then you can plug in time frequency building blocks and do the same thing and find out what the result should be. And so it's one of my ways of teaching these things is to say, well, I refer to geometric intuition. I try to put it down in MATLAB reality, so in something that I can compute. That allows me to give the results in full generality, but maybe with very slow, very expensive algorithms. And then I try to find structure in the corresponding matrices such that one can perform the same thing in a much better way. So that one may find out that the matrices coming up in Gabor analysis, for example, have a lot of structure. So in the old days, one could read in the papers, Gabor analysis is great, time frequency content is is meaningful. You know that the coefficient represents the information at that time, at that frequency. Meanwhile, we know so much more that we are not saying, yes, sorry, it's an non-orthogonal system, and because it's non-orthogonal, inversion of the corresponding matrix must be difficult. Now, you all know that there are a lot of non-orthogonal matrices where the inverse can be computed in a fast way, and nowadays we understand how to do it, and we can do a lot of things. So this was just some advertisement for GeoGebra. It's downloadable for free, and therefore we can also try these things. You can also look at the webpage of my linear algebra course if you want to do this. Now, in order to make sure that I do not forget to open a diary, maybe at the end you remind me of closing it, then I can share it with you. I was doing, I gave the diary a name, so my first command that I want to demonstrate to you, and then we go to real thing, is maybe this one. Okay, this is something to be remembered very easily because it's a beautiful picture. It's showing the matrix of the FFT of size 17. So it was created by the command more or less up to some formatting questions, plot FFT of I of 17. Now what you can learn from this is not only the nice structure of the matrix representing the FFT, but a lot of basic things. So what is I of 17? Well, I is just a unit matrix. So thought as a collection of vectors, you have the first unit vector, the second unit vector, the unit vector number 17. So it's a collection of unit vectors. MATLAB has the nice feature when you apply many commands that it works with vectors. So if it's applied, the FFT routine is applied to a collection of column vectors. That's what a matrix is at the moment. Then you get the Fourier transform of the first unit vector, the second, and so on. Well, we will talk about the pure frequencies, but the pure frequencies are the exponential functions, the complex exponential functions at the unit roots. So the points that are forming the edges, the convex hull, here are clearly the unit roots of order 17. So next thing is, what is the plotting routine doing? The plotting routine is showing you a collection of vectors. So it's showing you the individual Fourier transform of number 1, 2, 3 or so. Now, if you look a little bit closer, and that's a bit difficult probably from here now, you can see that some of these lines are every color that you choose is jumping in concrete distances. So the first one, which is probably not good to see, maybe, oh yes. The red one everything is starting at omega to the power 0. Now maybe I should take the pointer. So the first column, actually what is the first column? The first column is the FFT of constant 1. That's constant 1. That's 1, 1, 1, 1. So that's a point marked 17 times. You don't see it. But this next one is starting here. The red line here is starting here, going here. Probably it's not the second, but the last line because it's still visible. And you see that it's going up to here, but it's not closing because here you have. So probably the second is the green one, which is then at the end plot again overwritten by the red one. You can choose another one, let's say the blue one. It's jumping from omega to the power 0 to omega to the power 1, 2, 3. Then 6 and so on, you go on. Now you can imagine why I was choosing a prime number 17, because in this way you get a maximal performing a system with a lot of visible things. We can try out what happens if you do 16. It's less interesting. So 16, I would say, has fewer subgroups and so on, and therefore this pattern is not as nice. And if I would choose, I don't know, a big prime number, it would be just color. I mean, everything would be not visible. So what is, again, the plotting routine doing? The plotting routine is taking a collection of vectors, and this collection of vectors are plotted in the complex domain. And actually the plot is connecting the first value with the second value. So that's something we also will see when we are looking at sampling or so. Okay, now, so I'm going back from this very introductory course. You should learn what all this means, and I'm going back to basic linear algebra. Sorry for doing this at the beginning, but maybe we do simple matrices now. A is a random matrix of size k, so it's clearly a 5 by 5 matrix. Maybe I make it smaller because my displays. No, maybe change the display. Yeah, so it's better now. So C can be a random vector, which is take a column vector of format k. So C is a column vectors, and if I say B is A times C, then of course I'm getting a vector. Normal interpretation is you are saying a matrix of format M times M, Martha times North Pole. It's going from Rn to Rm. So it's throwing vectors from one place to the other. So that's very clear. It's the mapping that we have in mind is X. I'm writing X, and in MATLAB usually I write the symbol XX or so, but into A times X. Matrix multiplication in this case from the left. But when you're asking me what is it, then I take the opposite point of view. Usually I say, well, the vector is the person taking the decision. So I'm the vector X now. And here comes the matrix applied on me. And I'm saying, well, please, I'm ordering from you X times the first column vector plus X 2 times the second column vectors. Please make a linear combination. I dictate what the coefficients are, and you have to make the linear combination. So what is MATLAB doing is matrix vector multiplication or linear combination. So we know it's about linear combinations if I use the very natural notation of I from 1 to k in my case, to call the first or the ith column in a matrix with a little a with an arrow, then I'm doing a linear combination of this form. Now, when you want to say, I was doing this here, A is B with C, so if you have this here, then of course you would say, oh, I can solve it by, I can get X, the unknown, from this by dividing from the left with the B. And let's see what happens here. So X is A divided from the left from the B. And what is the norm of the original vector C minus the vector of X that I was getting? It's fine. It's numerically, it's practically 0. Well, what has been done? Well, it has what I have been doing. Dividing from the left is, of course, normally the same as I can also do this here, C minus. I have taken a random matrix, and the random matrix will hopefully be invertible or with very high probability, I mean probably 1, B, and that also gives us the same result, of course. Maybe not numerically, because the backslash command is in principle using the pseudo-inverse. So if I get not the same result by using the inf or the pinf, the pseudo-inverse, I would always trust the pinf solution, which is much more reliable. The other thing is, if I do something like B is random 5, maybe no, I take B equal A, I say, well, what if A would not be an invertible matrix, but a matrix which is a matrix not a full rank? So I produce out of my A, I destroy 2 columns, and I choose columns number 3 and 5 that are linear combinations of the earlier columns. So I'm making B, the third column is supposed to be now, I don't know, 2 times the first column. B and A are the same now. So minus column number 2. And I take B5 to be, for example, B3. Thank you. I should take my glasses. And I can add column number 4. What is the rank of the resulting matrix? Of course, it's just 3. It's this rank 3 matrix. How can I find what has happened? I just go to the row reduced echelon form. The row reduced echelon form, or just performing Gauss elimination, tries to say, well, I have a first vector. Are you linear independent? Yes, I see it's linear independent. Second vector, are you linear independent from the first one? Yes. Clearly, I mean, I could show you the B. I mean, with 3 eyes, probably you see that the second one is not a multiple of the first one. I mean, that's easy. The third one, is it a linear combination of the first 2? I don't think you see it with 3 eyes immediately. But the above thing tells you, yes, the relationship between the columns of the row, that's something I think is not so popular. The relationship between the columns of the row-reduced echelon form, the columns, and the original matrices is the same. I was choosing 2 times the first column minus 1 times, and I see it immediately in this. So I can also see immediately a linear span of these vectors is this here. So how does this matrix look like in geometric terms? I have one vector, which is my thumb. I have a second vector, which is not parallel. I have a third vector, I try to hold it in the same plane now. And then I have something, I mean, here I'm in R3 now, but it's this situation. What are we doing when we do Gauss elimination in a geometric way? We're trying to manipulate the first guy until it's the first vector, which is the x-axis. I try to put it here. That's the x-axis. Then I manipulate, preserving the linear relation such that the second one is getting the second unit vector. And when the linear relations are like this, everything, I see immediately what the linear combination is. So Gauss elimination is, after all, giving you a little bit more information than usually thought. It's not just determining the rank or a basis for the null space, but it's also giving you this. So, for example, N is the null space of B. And if I try to see what happens if I apply the row-reduced echelon form of B to N, what is the result? So you do not have everything on the screen. Numerically, it's clear that this is practically 0. So what has been done here? N is null. The command null is give me all the information about the null space. We have a matrix of rank 3 of format 5 by 5. So clearly, the dimension of the null space will be 2-dimensional. That's not surprising. So what does it mean to see these 2 vectors? It means we are getting an orthonormal basis of the null space. It's coming in the format of a column vectors. However, what I was doing here, I was multiplying it with this row-reduced echelon form. But remember, Gauss elimination is also can be interpreted as doing elementary matrix multiplication from the left. That means you are doing new linear combination of the rows. So this is another set of elements which is clearly a linear independent set because you have the unit vectors in the pivot positions. It's a clearly a basis plus some zero vectors. So what I was doing was doing matrix multiplication of these basis vectors of the null space with the basis vectors, basis vectors of the row space of the matrix, and then with the column space. But that means I was doing scalar products. So I was doing this following little experiment. You know that in terms of spaces, the null space of A and the row space of a matrix are perpendicular. And I was just trying to verify this numerically with MATLAB. Now, how can you get a projection onto the null space? Now, projection on the null space, that's another thing, is to remember that you can easily do it. Oops, it was the wrong comma. Yeah. You can easily do it in this way. Yeah, maybe I should, before I'm doing this, I should recall the following things. MATLAB is a program which allows to do matrix multiplication a priori. And you have, of course, also strings to write letters or comments, titles and so on. It doesn't even have matrix vector multiplication because you don't need it. Matrix vector multiplication is matrix multiplication with a matrix applied to a degenerate vector. Okay, that's very easy. Now, when you have two vectors and you would like to have a scalar product, and since we are here, so to say, as mathematicians, our tradition will be, or convention better, will be that the sesquilinear form is antilinear in the second component. So you would expect that you get, asking in an exam, k from 1 to capital K, x, k, y, k. If it's complex conjugate, you should use this. Now remember, in MATLAB is the harmless command is this prime is easy to type, at least on an American keyboard, and that's the more important command procedure in all these things. It's not just transposition, but conjugation composed with conjugation with transposition. So if somebody is giving you two vectors, now I have to say this is y and this is x, how do you get scalar product? Well, you turn one into row vector position, but that's the y, so maybe you should think like this. That's the y, and then in MATLAB you can realize it as y prime with x. Side remark, I personally work a lot with row vectors. Hopefully I will not confuse too much by jumping between row and column vectors, because you always can interchange one for the other. But one of the reasons why I like to work with row vectors is that in that case you would have keep the order in a very natural way. But at the moment we're at the introductory phase and you just think, that's how I learned. Scalar products are these objects and I can realize this here. Now, if somebody is giving you a matrix, for example, B, and you would like to verify what the scalar products are, yeah, I mean, you invest the possible orthogonality of the matrix. So, for example, I call it GB now. That would be, in my case, G prime with B. So why is this the Gram matrix? Why is the collection of all scalar products easily written as B prime with B? Well, look at the position that you have here. What is happening in row number 3, column number 5 or so? You take matrix vector multiplication, but first you take the two matrices. You take the first one in transposition. So what happens if I take, let's say, thumb with thumb, position 1, 1, is first column turning into first row, but conjugate, multiply it with the first column. That's the scalar product of B1 with B2, B1, and so on and so on. So if I want to verify that a given matrix, for example, N is an orthonormal matrix, I can create sorry, I can look at n prime with n. So n, remember, n was in my case so far the orthonormal basis for the null space. So these were two column vectors in R5. So I'm looking at the scalar products that they have, and clear enough, these two are orthogonal to each other. So okay, they are really an orthonormal system. On the other hand, if I want to write the projection operator, so n in my standard notation would be a collection of, in my case, of two column vectors in R5. So what is then the projection onto this column space of any vector x? You would say, okay, I have to take a sum. Maybe I write it out in detail. I take scalar product of the vector on which I apply with the first normal vector, and then n1 plus x with the second one. Well, you can say, well, what I have to do is I have to take from x to the collection of scalar products, and from that, by synthesis, summation, I do the summation of these coefficients with the linear combination. So how can you do it in MATLAB stepwise? You would say, okay, x is a column vector in R5. It has to undergo multiplication with n star x. Remember, n are two column vectors. You take them into horizontal position, do matrix multiplication, you have exactly the coefficients. With these coefficients, you are doing synthesis. You are doing n with n prime with x. That's what we are doing in order to really write down the projection onto a subspace having an orthonormal basis. And because of the associativity law, the matrix is just n with n prime. So just to convince you that, I mean, what I called Pn, once more, is a projection. I say what is the norm of Pn minus Pn star, Pn with squared. And then it's, in the operator norm, it's numerically practical 0. Well, it's no surprise, because if you write it out, it's what is it? N with n prime, with n with n prime, and the inner two are of course cancelling out, and we have seen it there, the unit matrix. So it is an idempotent. It's clearly due to symmetry, a symmetric idempotent. Therefore, it's an orthogonal projection operator. While we could go on and verify that's exactly the orthogonal projection onto the null space. We could also say, that's now a bit risky. O is the orthogonal basis now of B prime. Now you see O is a system of 3 column vectors. O with O prime with O. Is it an orthonormal system really? Yes, it's an orthonormal system. If we do the projection, we have to change the order, so it's O with O prime. So A prime is first, doing first coefficients with the orthonormal system, then synthesize. What is PO plus PN? Looks quite good. It's the sum of 2 projection operators, and it looks very much like the unit matrix, which means, yes, we have the splitting. For every matrix, you have the situation that the null space of the matrix and the row space are perpendicular to each other. So now I have to get out my pencils, which I forgot to prepare, but I think I will. Yeah. So the basic thing about matrices of full rank, some of you have seen it already, is the following. We're talking about a matrix. In my demonstration, I can use only a matrix 3 by 3, which is not invertible because it doesn't. Otherwise, it doesn't have a null space. So what I usually do is I take a matrix which has rank 2. So actually, another favorite matrix would be, I call it T for test matrix. I put a zeros of size 3. and T, the positions I put 1 to 9. That's also something where you can learn a little bit of MATLAB, which means you're filling in the vector 1, 2, 3, 4, 5, 6, 7 to 9 in the matrix. So there's an empty box, so to say. Format is 0, 0, so format is clear. Now you're filling in a vector with length 9 into a matrix. I mean, how should you do it? Well, a matrix, remember, is a collection of column vectors. So the first column vector is clearly the one that you start with. So you start 1, 2, 3. Then the next column is 4, 5, and so on. So, question, what is the rank of this matrix? Rank of T is this. T4 is, I have a MATLAB routine to do it for you. So what is the rank of this T4 option? Bits. Who is suggesting something? You're saying 2? Other people having other options? No, it's always independent of n, it's always 2. Why? Because it has so much regularity that clearly the difference between the first and the second column vector is constant, but that's true for everyone. So you just say, well, I can produce the constant sequence 3, 3, 3 as a difference of the second column with the first, in the first case. In the other case, the other multiple. And then, of course, it continues. It's even true, the same is true for the row vectors. So you have, in the 3×3 case, a very nice example of a matrix of rank 2. You can ask, well, is it normal? Well, very easily you check T with T star and T star with T. Are they equal? Evidently not. So it's not a normal matrix. Do you think that the row space and column space of these two matrices are the same? Probably you would say, well, I have to check what are the null spaces or so. But because of this similar pattern, it turns out they are equal. So it's an easy exercise, good exercise actually, to find out for normal matrices, row and column spaces are the same. That's exactly why you can do the eigenspace decomposition and so on. But it can happen, of course, that they are, for other reasons, equal. So this is the case. Now, when I go now with this matrix T, and just so that you have one possible example, which has rank 2, then it's clear that the target space, so the linear span of the columns of this matrix, will be a plane. It's also clear that the null space will be one-dimensional, so this is one-dimensional. What we have seen is that there is an orthogonal complement to this null space, and this orthogonal complement is the row space. So you should imagine there are three vectors spanning the two-dimensional plane, which is perpendicular to the null space. Clearly, for reasons of symmetry, the column space has the null space of the transpose matrix here. So in this situation, all the geometric information that we need for linear algebra or so is in these 4 spaces. Most of you may know the course of Gilbert-Strang. He's calling Gauss the workhorse of linear algebra, and he's calling these 4 spaces maybe the most important thing for linear algebra. Now, why is it so important? Because, as you can see, this and this fits very well. Remember, row rank equals column rank. Why are these 2 spaces the same? I think it's, personally, after a while, I thought, it's magic. I mean, you can give me a 10,000 by 10,000 matrix. You can be very nasty. Put any numbers into this system. You determine the dimension of the space coming from the rows and from the columns, and they're equal. Well, why are they equal? Well, you probably have seen that I have thrown away the null spaces. Well, what happens if I do formally, if I look at my mapping from null space with row space, I map it into the, take the image now. I restrict my linear mapping to the row space. Would you say anything is missing? No, I mean I have missed vectors which are thrown to 0 anyway. So if you give me any vector, it will be something in the row space plus something that disappears, so the images are the same. So I'm getting the same thing. If I take the restriction, is there a chance for a null space? No, the null space can be only the intersection of the original null space with my restriction domain, but there is nothing, there is no vector which is perpendicular to itself except the null vector, so this must be an isomorphism. So restricting the basis, I mean the mapping to the row space must be an isomorphism, and that's why row space and column space have the same rank. Okay, so that we are already in a good position, but now somebody is giving me a not solvable equation, ax equals b. How can you solve it? I mean, you're maybe telling your students, well, if it's a rectangular equation system, you cannot solve it. So you have ax equals b. But if this is not in the column space of the matrix, so, well, if I want to do something, I want to get something, and I cannot get it because my resources are not strong enough, should I give up my wishes? No, I try to reduce the wishes to something which is possible. Of course, I want to modify it as little as possible. So one is a linear system, one is an equation consistent. Well, if I'm in the column space, so you're asking me the B, which is outside of the column space, and you want to have some replacement of this system by another system which is possible that you can solve. Then it's clear, I mean, from this position out, that you just project it in an orthogonal way. So given the right-hand side, we have to say, well, I'm sorry, it's not okay, but if we project onto the column space, in this case, of course, of B, it will be consistent. We make a minimal error. Okay, so I'm throwing away this part which is in null space, and you think you see just the red dot in my hand here. Now we know that this red dot has, on the other hand side, a green point, which is one of the possible solutions. But you also remember that the general system of a non-inhomogeneous linear system is the specific solution plus an arbitrary solution from the null space. You can add everything to the null space. So the question is, what is the nice thing with this vector here? Well, look at this from this point of view. You have 0 here, probably somewhere here. This is the inhomogeneous solution. If you take any other vector, Pythagoras tells you that the cost must be larger. So if I have decided my big wish is cannot be satisfied, I cannot buy the supercomputer, but I can buy a decent notebook for a certain, with a certain equipment. Well, I find out there were many possible ways of getting my solution. There are many possible shops where I can buy this computer. What are you doing nowadays? You're going probably to the internet and you look for the cheapest solution. What is the cheapest solution? Well, the shortest vector, the smallest. So clearly I'm talking in this case about minimal norm least square. Or if you want, I'm talking about the pseudo-inverse, because that's exactly what we do. So among all the others, so x equals pinf of A times B, and that's what you get with this slash operator. You're getting exactly, in a nutshell, this cheapest solution. So somebody is giving you a vector, you replace the system by the best possible, which is consistent, and then you choose the vector with minimal norm. That's more or less what is happening, and how you can interpret the pseudo-inverse. It's also clear that, in mathematical terminology, of course, we write A plus for the pseudo-inverse. Every matrix has a pseudo-inverse, and if you combine, for example, the pseudo-inverse with the matrix itself, for example, somebody is applying the pseudo-inverse where think of a mapping going from Rn to Rm. So the pseudo-inverse is applied to vectors in Rm. The B must be in Rm. You apply the pseudo-inverse, it means you project it here, you move it over here. And then you apply afterwards the mapping itself, the matrix. So where do you get? You get back to this here, so it's the point in the, so it's the projection onto the column space. If you want to know the projection onto row space, it's exactly this. So maybe we can try to play this here. We can say that we have the PO, which was the projection onto the row space, and we can try to say, well, this should be the same as if I'm on the row space, I have to apply first the pinf and then the matrix. So in terms of writing, I should probably write A and then pinf of A. I'm not sure. No, that was stupid. First of all, it's B. It should be B. That was the error. Okay, yeah. So I've kind of done it too quickly. I don't want to play around. So probably I was just using the projection on the wrong space. But the point is, with the combination of pinf of A or A prime, you can get all the corresponding matrices, projections also. I should not play around too much with this now. Now, okay, so I think, yeah, maybe this is the next thing I would like to mention is the singular value decomposition. So of course, if you are doing U as V is SVD of B, then you can see that in this case you are getting this well-known factorization of a matrix. So the call is U as V equals the matrix. In our case it was B, or SVD of B, means that you are taking getting a representation of the form that, well, you write it as U with S with V prime. Now, where U and V, so maybe this is an M by N matrix. And so this must be, I always tell my students, it has to be domino principle. It must be M times M, it must be N times N. And therefore it is here a M by N diagonal matrix with the singular values. Here it's square, so you don't see what is, I mean, M equal N equals 5. But why, and then these are unitary guys, so unitary matrices, unitary. But with V, also V prime is unitary, so why do people write V prime? Well, if you write it out, it tells you that B with X can be written in a nice way. K from 1 to N. If you're giving me in a 5-dimensional space 5 vectors and you turn it around, you're doing matrix multiplication. Remember what I was writing here on the first blackboard. I'm taking scalar product, so it tells me, well, the natural alphabetic order U and V is how you write it. But the way how you locate it, and also the domino principle tells you, well, if the matrix is mapping vectors from Rn to Rm, you first have to start in the Rn domain. So if somebody is giving you an orthonormal basis in Rn and some vector, then you can take the scalar products. Then you can multiply these scalar products with numbers, which are the singular values, and then you do synthesis on the other domain. I'm in the Rm now, so it's quite well fitting. The V prime action is saying, okay, I have to take X with individual vectors from the system. Then I have to multiply with Sk, so it's scaling factors, and then I have to do synthesis with these vectors here. So whether you are saying every linear mapping can be written in this way with an orthonormal system, or whether you are saying that you have the singular value decomposition, is the same thing. Again, in this simple example that I had before with rank 2, you can even make a very easy experiment of thought. You can say, well, somebody is giving you a two-dimensional row vector. Somehow, how can I describe the mapping from the row vector to the column vector? So from a two-dimensional space to a two-dimensional space. Well, and I'm searching for an orthogonal basis here, such that it's mapped on an orthogonal basis on the other side. There's a nice. There are also nice MATLAB routines to demonstrate this. I'm just doing it by hand now. So again, idea of thought, experiment of thought. How do you get all possible orthogonal systems here? Well, you take one and then you rotate it. So take a random orthogonal system here. You look at it under this matrix. You look what it is, and you see, okay, it's acute angle, for example. Then you start rotating it, and you watch what happens here. You can imagine when I rotate in a 1 degree, and this is always acute, I will not have the chance to fill the whole circle. I mean, I have to go around somehow. So you will watch that it's changed the shape, and at some moment, it's an obtuse angle. So if I have acute opening up, there must be a position where orthogonal goes to orthogonal, and that's the right moment. Of course, in practice, we know what you have to do. You have to take the Gram matrix, B with B prime or B prime with B, do a diagonalization of that matrix, take the eigenvectors, move them from this position to this, and in the null space, you take arbitrary Gram-Schmidt orthonormal complements, which actually don't play a role, because if the S is 0, whatever you take will work. So it's just you complete your orthonormal system for the row and the columns vector, so they have to be matched at the level of a rank R isomorphism. So every linear mapping, as I tried to convince you, is an isomorphism between two R-dimensional spaces. Rank is the R. The rest is 0, and then the magic thing with SVD is you can even choose an orthonormal basis such that this is true. Okay, so every matrix, thanks to the singular value decomposition, has such a representation. And now the question is, what is B plus? And B plus is evidently trying to invert this procedure in the most natural way. I told you in my case the matrix is 3 by 3, but in reality it's mapping the row space, two-dimensional plane into row space. So the pseudo-inverse is just undoing this. You're going from column space to row space, and for the rest you cannot say anything. And the S plus, of course, what is the S plus? Is the rectangular matrix of the corresponding format. It's M times N, and where you have S1 and SR, 1 over SR, and the rest is all zeros. So the orthogonal complements cannot be inverted. But on the part where you say, well, this orthonormal system is going onto a modified other orthonormal system, you can match it. If the factor is singular value is 2, it's a vector of length 1 going to a vector of length 2. On the way back, it has to be it has to shrink, of course. The fact that you can do it and that it's efficiently implemented is a great thing, but that's, so to say, not so important. So I think what the take-home message for this part is you understand the linear mapping by the action on between row and column space, and sometimes you can get a bit of more information by saying you can even describe it by orthonormal systems. But it's not really necessary for other things, because just the splitting of the two spaces, the orthogonality of row space and null space, for example, are already quite good. There's another further message that I usually mention at this point. You can fabricate, I mean, if somebody is giving me a matrix, this viewpoint tells you it's a collection of column vectors. No, it's also a collection of row vectors. If you have a matrix, you can build A with A prime. You can build a pseudo-inverse of A or pseudo-inverse of A prime. You can start building alphabets and gluing it together. As long as domino allows you, I mean, as long as the dimensions are okay, I can take the pseudo-inverse of a matrix and multiply it with whatever fits, and so make long chains. The story is that each of these spaces has a dimension. So it has a null space and a target space. And all the target spaces, all the null spaces that you get are always the same 4 spaces. So you're not getting anything new. So what is the target space of the A prime? Okay, I'm A plus, the pseudo-inverse. You're going from the Rm back to the Rn. What is the target space? The row space of the original matrix. What is the null space of the pseudo-inverse? Well, it's of course the null space that you had here. So it's the null space of the A prime. So that's also quite helpful in certain considerations. If you take, for example, the Gram matrix, which is quite useful here, it's usually understood as a tool to find out whether a system of vectors is linear independent. So if I give you 3 vectors and you want to know are they linear independent, you can say, well, I check is the Gram matrix invertible. Well, what is the null space of the Gram matrix? It's starting in the same place where the B is starting. So the null space of the Gram matrix is the same as the null space of the matrix. What is the advantage of looking at the Gram matrix? This is a square matrix. It's invertible if and only if it's surjective and so on, or if the determinant is. If you have 3 vectors in R20, you are not worried about the big dimension. You're just having 3 by 3 matrix to inspect. So in that case, it's really very practical. Okay, so I think these are the things that I wanted to tell you first. And then the next thing is to come to the complex domain. We have seen that the FFT is using a lot the unit vectors. So I have a routine called unit roots of order n. So maybe we take order 5. And I do a plot of this here. Then it's not very nice because it's not in the right format. Axis square, maybe a grid, and show graphic. Shows you that you have points which are in the plane, but maybe I want to show it a little bit better. I make hold on, plot unit roots, but now as red stars. Hold off, show graphic. And then you see at least that these are probably and in reality the unit roots of order 5. So you can say, well, 360 divided by 5 and make the corresponding starting with 0 or so and so on. Now, what you also should know or recall is what MATLAB is doing with polynomials. So how is MATLAB storing polynomials? Yeah, or maybe as a side comment, I'm trying to go through linear algebra 2, which means eigenvalue analysis. So if somebody is giving you a matrix A, or yeah, we can take the matrix A, how do you start or how do you explain eigenvalue analysis? So how do you find the eigenvectors and all these things? Yeah, just tell me. First step. Characteristic polynomial, yeah. How do you get the characteristic polynomial in MATLAB? Very easy, you just say P is poly of A. And poly of A is giving you apparently a sequence of numbers describing, well, it's 6 numbers. Well, but 6 numbers is good because it's describing a polynomial of degree 5. So what you know about the characteristic polynomial, it is clearly a polynomial with leading terms, in this case lambda to the 5th. And the rest is apparently coefficients. So what can we learn from this harmless command? It's telling you MATLAB is implementing the coefficients in the order of decreasing order. So the highest, the first term that is coming. Now, in some cases, it's in slight conflict with some other conventions that we will see in a moment with the Fourier transform. But otherwise, it's quite fine because if I want to evaluate, yeah, maybe I'm taking, I don't know, C was a random vector. So remember, C was a vector of length 5. And if I want as a basis linear spacing from -2 to 3 with, I don't know, 500 points. That's just, oops, lin space. Yeah, exactly, the E was missing. So I get a linear arithmetic progression with 500 points, so not 1 over 100, but 500 points, including the last ones. And if I plot over this space the values of the polynomial with coefficients coming from the coefficient C and at the positions B, then I should see some polynomial. Yeah, okay. It's not very nice, but also not very surprising. Why? Because I was choosing random, meaning in the interval 0, 1, so non-negative coefficients. And clearly the higher order term is dominant in this thing. But you can imagine, you can at least plot polynomials in MATLAB by saying, I want to plot the polynomial with these coefficients, so I have now the polynomial at the points. And if I want to have not just labels from 1 to 500, this was the first value, the second value, the third value, but the right position, so it's really correctly labeled from -2 to 3 in my case. I just have to say, at the basis element, I have to do this. I can do, of course, fancy types of plots. I can zoom in, I can show you, which is not important now, that this is piecewise linear interpolation between the values and so on. Now, what is another thing is harmless version. What is polyval of 1.123 at 10? Clearly, that's 123. When you see 123 somewhere, and it's maybe the price of, I don't know, a hotel room or so, then you know it's 123, and it's 1 times 100, 2 times 10, 3 times 10 to the 0. So it's very natural to say, well, the length of the vector already tells you. I mean, if you see a big number, then leading zeros can be ignored. If I would write 0, it would say, yes, clearly it's not 0 times 1,000 euro, but it's just 1 times 100 and so on. So the length of the vector tells you the degree of the polynomial in decreasing order. So that's very natural, but it's, as I said, mentioned, not the same as with the MATLAB routine for the Fourier transform, because what I claim is that the Fourier transform matrix is more or less, maybe I do first now the Fourier transform matrix of FFT matrix of size 4. Yeah, okay. Maybe, yeah, we can just look at it. Fourier transform matrix of size 4 is 1, 1, 1, which is clearly x to the 0, which is 1, at all the possible unit roots of order 4. X to the 0 at 4 points. The more interesting one is the second column. The second column says we're starting now with x to the power 1, and we get the value at 1. We get the value at minus I, sorry. We get the value at here, and we get this. So I is the fourth root of -1 in the natural way. I mean, in the mathematical positive sense, you would say I is the primitive root of order n. And what the Fourier matrix is showing us is minus I, so it's showing us 1 minus I squared, which is of course also -1, and it's showing us I. So it's showing us the unit roots of order 4 in the clockwise sense, or the conjugate of the ones in the ordinary sense. Let's check if this is true in the other one. Of course, unit roots of order 4 to the second power give you +1, -1, +1, -1. And if I take the last one, then you see this is now in the positive sense, which is of course the last one is the conjugate of the first one. So you start from here, and you're going in the mathematical positive sense through the unit root of order n. So if you would, maybe we try to go plot this unit roots of order 8 maybe, FFT of I of 8. Axis is square. Then you can already get an idea what is really happening, because the first column, probably in red and not visible, is the point 1, 1, 1, 1, 1. Yeah, I should also, yeah, maybe I show you. No, I think the numbers you cannot read off. We can look at the plot. The last thing that was plotted is unit roots of order 8. The primitive unit roots of order 8 is this one. It's 45 degrees. So 360 by 8 is 45. That's why I think for courses this is the best choice, because this is something that you can do with freehand plotting also. What you see here is going from omega to the first power, second power, up to the power 7, and the 8th power would be original. That's why the green part is left over. So the first thing that would be plotted would be here in the clockwise sense until here, but it stops here, and then at the very last moment it's in the opposite way. So what is then one of the things that is coming here? That would be the second last one. It's still in the opposite direction every second, from here to here to here to here. Is it ending here? No, it's going here to here to here to here. What is the good or interesting part? If somebody is giving you the unit roots of order, unit roots of order 8, these are, there's a typo now, now you see all these unit roots of order 8, but then I'm taking the point, the square of these. So the command to take from a vector, going from a vector x1, x2, x3 and so on, to the pointwise square of it, it's just this point hat 2. So I'm taking pointwise squares. And you are of course saying, well, it's ridiculous. It's clear that the squares of the unit roots of order 8 is just going through the unit circle, but at double speed, which means I'm going 2 circles. And clearly it's unit roots of order 4 coming up twice. But that will be relevant for Fourier transform applications. Why? Because there is a connection between polynomials evaluated at the unit roots of order n and f of t. So that's the thing that I will try to point out at least a little bit. So what is a routine that I'm using very much, and I will try to explain this to you. What is the comp norm routine? It's a kind of private routine. So comp norm of 2 vectors. You give me a vector u and a vector v. In concrete situation, it might be u is a vector that I have computed in a traditional way using, I don't know, big matrix inversion or so. And v is a vector which I try to compute with a fast algorithm. I'm employing some FFT tricks or other things. And I look at the functions and say, oh yes, great, this is really the same. And then I observe, well, it's the same up to a factor 4. Why? Because for some reason I was forgetting a constant 4. So comp norm is the harmless routine. It measures the norm between the normalized version of a vector u and a vector v. So it's not part of standard MATLAB, but of course you can download it from our site, and I'm using it all the time. That's why it's good if you have seen it. So, but also the output tells me, well, if the vectors are not the same length, it tells me what the factor is. So the output has 2 lines. The first saying the quotient of the lengths of the 2 vectors is 1. That means they are really the same. In this case, there are 2 matrices. 2 matrices, and the matrices are taken as vectors in Rn squared or in Cn squared. So I have 2 matrices. These are vectors in C to the exponent 64, because a matrix of format 8 by 8, there are 2 such matrices, has of course 64 coordinates, and they are complex numbers. And actually, if you don't remember, we have an isomorphism between the n times n matrices and Cn. Well, every orthonormal basis for the linear vector space of n by n matrices is providing such an isomorphism. But again, if I take my T And you remember, sorry, T3 I think was this. Okay, T3 is, I put my test matrix here, but maybe I've not baptized it. So if this here is, how can I get the corresponding vector? T3 of course. I take T3 into this format. So it's saying, well, you're giving me a square matrix and I have to read out all the columns. Well, I have to choose some order. How to read out? Best way, first vector, down, second vector, third vector. That's the best choice. So you can say, yes, the basis is the one pixel matrix which has one pixel in the first position, then the second one is this, and that's the coordinates in this spaces. It's a complicated way of expressing it. But everybody can understand that if you have this. Now, if you want to have the norm of this matrix, this norm is some number. It's a complicated thing. It's the operator norm. It's applying the matrix as a mapping from R3 to R3, knowing that this turns a cube, a ball into an ellipse, and the main axis of the ellipse has some extension, and that extension is 16. Well, that's complicated if you have large matrices. But you can say, no, what I really want to do is a norm of that vector. So I say, well, take it the norm as a Euclidean matrix, as an element of the Euclidean space. So actually it's not far away from this. But there's another command which you also might not know from daily use, is the so-called Frobenius norm. So the Frobenius norm is really just the norm of the vector. Now, probably because you have this background in harmonic analysis, many of you, or in Fourier analysis, you have learned about Hilbert-Schmidt operators. So what are Hilbert-Schmidt operators? Well, these are certain compact operators which have a singular value decomposition L2, and the good thing is Hilbert-Schmidt operators are made such that they have a scalar product. So there is the Hilbert space of Hilbert-Schmidt operators. What is the Hilbert space norm? What is the scalar product? So you give me two Hilbert-Schmidt operators, S and T, and you can define it as the trace of S with T star. So you compose T, in our case it would be matrices, it would be the transpose conjugate, and you compose the two matrices. Now, so what we can say is here, we try to see what is the square root of the trace, and trace is just the trace of a matrix, of T3 with T3 prime. It happens to be the same number. Well, it happens to be the same number, or it's just a generalization. Well, it's just a generalization. Is it a good way to compute it in this way? Even if you learn it in functional analysis, I wouldn't say so. It's not very efficient. You are computing a matrix product. So for a 100 by 100 matrix, you are computing 10,000 scalar products. Why? Because you want to do the trace. What is the trace? The sum of the diagonal elements. So you need not 10,000, you need 100 entries. So making the full matrix and afterwards taking this is nice for analytic computation. Of course, one has to know, but I would say whenever I see nowadays a Hilbert-Schmidt scalar product, the Frobenius norm, or a Hilbert-Schmidt object, I say, well, it means matrices are, in the finite dimensional setting, just entries of a larger space of C n squared, or if you want, C n cross m. And as such, there's a Euclidean structure. So for example, if you're giving me a 3 by 3 matrix, it's an element of R9. And you can ask me, is there a closest nearby unitary matrix? Then I'm thinking, okay, I have to find an orthonormal system which is not far away. But we have a clear concept what closeness means. Of course, we cannot imagine R9, but we can imagine we do computations in R9. So the question is it an easy task? And then, of course, you say, oh yes, maybe we take this idea, we have a convex set in an n-dimensional space, there is a closest point. Well, unitary matrices are not convex. If you do linear combinations of convex matrices, of unitary matrices, you may end up with a non-unitary matrix. So it's not that kind of approximation. But still you can reformulate it, and then you come again to this thing that I tried to explain at the very beginning. Yes, there is a best approximation that you can write down. I have to eliminate a little bit of the blackboard. So, given an n by n matrix, I would say for simplicity I make it real for the explanation. N by n real matrix, and which is invertible, so we know it's a basis. Then there exists a uniquely determined orthonormal, so maybe I call it an orthogonal matrix, remembering that this is bad terminology, and orthogonal matrices are not matrices where the columns are an orthogonal system, but they are orthogonality preserving matrices. That means their columns are an orthonormal basis. That's why I prefer to say, I will still say it's a real unitary matrix. U such that A minus U in the Hilbert-Schmidt Frobenius sense or so is minimal. And what would be a natural way to describe it in a geometric way? Geometrically, I have the following situation. You are giving me 3 vectors in R3 in general positions such that they are bases. This is kind of a case of acute angles. It's clearly they are not orthogonal to each other. So how can I modify it such that hopefully I get an orthogonal basis? Well, I have to move these vectors. Let's assume they are length 1 for fixed lengths. Well, I have to move them, and I could say, well, how far they have to be moved, that's part of the distance here. So I can say, well, this one I move a little bit in this direction. So I have an error, a movement of this distance. This one has to be moved this. Maybe if it's too long, I have to shrink it just. If you give me an orthogonal matrix in the sense of orthogonal vectors which are too long, you shrink them to the correct length or so. And the third one is also. Now, that means I have 3 movements. How can I measure the total movement? Well, I take the Euclidean length of this vector of 3 distances. Well, if you recompute everything, you find out that's exactly the Hilbert-Schmidt distance. So geometrically, the Hilbert-Schmidt minimization tells you, I want to have movements of the original positions to the new positions such that the length of this movement vector, the Euclidean length, is minimized. And then, of course, you can say, well, can you solve this minimization problem? And the answer is, recall the polar decomposition. The polar decomposition is, roughly speaking, the following idea. I can decompose every matrix into a product of every invertible matrix. Yeah, that's why I also put this condition in a product of a unitary matrix and this rescaling matrix. To understand the principle, it's quite good to say, well, let's look at the 1 times 1 matrices. 1 times 1 matrices are numbers, well, complex numbers. So I'm giving, or you are giving me an arbitrary invertible 1 by 1 matrix. What does it mean? You're giving me a point in the complex plane, which is, so it's an element of 1 by 1 matrices, and so it's an element different from 0. What are the unitary 1 by 1 matrices? Well, these are the matrices, the number set, such that set transpose conjugate, transposition is trivial, so conjugate is the inverse. So what does it mean that u times u bar, which is of course u bar, is 1? It means that you are on the unit circle. So this is clearly the unitary group of 1 by 1 matrices is a unit circle. If you want to know what is in the Euclidean distance the closest neighbor here, you're just saying, well, I take polar decomposition. You take the angle part and throw away the decomposition. Okay, so why is singular value decomposition useful for polar decomposition? Well, you write your, it's now my A as U as V prime. And depending on your preference, you can do the unitary part in front or at the end, but it's always the same. You can say, well, this U prime would be nice. It's a pure scaling. It's a scaling in the direction of the U system. But then the remainder is U V prime. And if you prefer the other one, then you write U V prime times V with S with V prime. So either part is a scaling part containing the S here, but the common part that is the unitary part is just U V prime. So that's the way how I do it. My art best, because I really think it's the best way, provides this solution. And I think it's interesting, and I'm grateful for further hints. It's called, in our context, the Loewdin orthogonalization. So it's going back to a theoretical physicist who was using it. But I also discovered in a book edited by one of our colleagues from the Technical University, Professor Stachel, so Philip Gross may know him. And in his big book on basic mathematics, is a really nice book. And I was asking him, and he told me, yes, he was needing it for applications in robotics. So I'm quite sure that it's a very natural way of orthogonalization that one can use, and I will use it in concrete contexts then. At the end, I must say, the first time I met this construction was in the book of Yves Meyer on wavelets. And there he wanted to say, well, I have a system of translates building up the scale space. And if they are not orthonormal like the B-splines, they are overlapping, they cannot be orthonormal, I would like to do an orthonormalization which respects this group structure. Then it's exactly this construction in the background. And how do people describe it? It can be described via, and I don't want to do it now, but the gram to the -1/2. So somehow, that's maybe a good exercise for until tomorrow, that you look a little bit of how can this be connected. I mean, I tell you as a simple trick of getting the best unitary approximation of a matrix, do singular value decomposition and pull out the dilation part and throw the rest will do the job. The other way would be, no, I'm supposed to take the matrix from the gram matrix. Can write the matrix, the ground matrix in SVD, and then you have sigma coming up twice. That's why you have to kill a sigma squared, and of course sigma squared to the -1/2 is more or less doing the job, and that's giving you exactly the same thing. So it's the same trick. When you are in a concrete situation, few vectors in a large space, of course you should make it with the gram matrix. You should not do singular value decomposition. But if you are in a general situation, maybe this way of understanding it is much better. Okay, so I'm coming close to the end. I want to tell you two things. Maybe one which I will repeat, and another thing which I want to do some short demonstration. So there was this question, and I was going from here to a long discussion. I want to, this short experiment shows you that two objects are the same. Here it is the FFT matrix. So the matrix doing the FFT. So FFT of I of 8 is in principle the 8 by 8 matrix that you can apply to a column vector, and you will get the FFT of that vector. There's a flip left right, which has to do with the fact that in this matrix we have seen that the constant 1 is coming in the first position, but on the other hand, the polyval routine is so that the last order is at the end. Okay, here I'm having the unit roots of order 8, so this is a vector. have 8 points on the unit circle. What is the natural way of programming such a thing? Of course, I'm doing it with the exponential function or so, but the order, I mean, I go to the unit roots of order 8 in the mathematical positive sense. Where do I start? I start with constant 1, first primitive unit root of order 1, and so I'm going this way. So that's what they are. But as we have seen, one should go in the opposite direction. I mean, plotting the FFT matrix means we have to go in the opposite direction. So we still have a collection of points. And what is then the fundament matrix? The fundament matrix is the matrix that describes how to get from the coefficients to the values of a polynomial at a collection of points. So, and we can check this also, this is something also you can check yourself, that either making polyval of a matrix with these things and some coefficients, or doing matrix multiplication with the fundament matrix. And of course, this fundament matrix has to be compatible with the polynomial evaluation of MATLAB. And that's having the leading coefficients in front. That's why we have to have this flip, and why by the convention we have to go in the opposite direction. You also may remember that when you do Fourier analysis, and that will come up in many things, you have the minus in the exponent when you do Fourier analysis, and you have the plus when you do synthesis, which is great, because it really means that FFT is the Fourier analysis operator. You're taking scalar products with respect to the pure frequencies. When you're doing synthesis afterwards, it's synthesis. So it's good that this convention is okay, except from the order. So this is one thing, and from there you can get many other properties. So the last thing that I would like to mention to you is the question of finite sequences. So when we are dealing with MATLAB and real things, we are always we're reading that engineers say in the finite case you have to work with vectors, so with finitely many samples. So when I plot the Gauss function, our discrete Gauss function to you, it's looking like this. So maybe I adapt the axis a little bit. So that's not so nice, and I prefer my private plotting routine plot centered, the same object, just plotted in a different way, and that's with different labels. And just to demonstrate, because that's better, that's good for discussion, I was producing a very primitive model of a Gauss function on the unit circle. So it's on the unit circle. And I have 2 copies. And now I'll show you what MATLAB is doing. MATLAB is having a function on the unit circle. It has to cut it at some place. So unit roots are arranged in some order. So it's plausible that the cutting is okay like this. So the first component is the one at omega to the 0. When is a function symmetric? Of course, if the value at 0 can be anything, but if the second coordinate equals the last one, if the third component is the third one. So it's not flip left, right. I mean, for big N it's no big difference, but numerically this is 1. How would you want to see it? Well, you would like to keep that impression intact, so I'm cutting on the opposite end. It's always the same function. It's a periodic function. I mean, I cut. The data are still the same, but when I plot in this way, and you have the labels. So that's the plot C routine, and that's the plot routine. And there's no difference in the data. I mean, I was cutting the same. I mean, I'm trying to make 2 identical copies. And the same way you will see then corresponding images or so, but I think that can be done in a further way. So we have to understand that when we are doing Fourier analysis, either we are going from coefficients to values of polynomials on unit roots, or we are going from continuous functions to functions on the torus or on the unit roots. But how the translations has to be done, one has to be careful. That's not completely trivial. And there are even very relatively good books, I would say, which talk about pitfalls and problems that you have to observe when you go from the general abstract theory to the concrete theory. And sometimes I'm saying, well, yes, you have to fight symptoms if you are doing a bad translations. And I can explain some of these things in one of the next courses. So try to take a harmonic analysis point of view, saying we know that Fourier analysis can be done on a variety of locally compact abelian groups. That can be the real line, the plane for images or so. It can be the cyclic group of order n or so, and all these things. But when you translate it, try to be careful in your translation. And that's maybe the second take-home message. And so I will continue with general frames and so on tomorrow. Thank you very much.